So first we try to investigate first the definition. What do you mean by stress at a point? Because now, as I told you in the last class, that what exactly we try to pretend, we try to assume that the simplest case that I am discussing, I think I am repeating again because those who are absent last class. So if simple bar is subjected to axial load and we want to investigate the stress within this particular bar, we take the free body of this, we cut this section, we try to visualize the stresses acting over this cross section. And of course, the intensity of this, the force distributed over the surface, we call it stress. Okay, and of course, what is the resultant of this smaller distributed forces acting over the cross section? Resultant will of course be, because the body has to be under equilibrium. Okay, and then we can say that this force has to be sigma times cross sectional area, and this is how we define, because the resultant of this smaller distribution, that should be equivalent to the external force. And from this equilibrium equation only, like this is a very simple case where we have to write the equilibrium equation, get the resultant, but this is how define that, how to define this intensity of this smaller distribution of the forces, we call it stress, that is force upon area. Okay, now what we want to do is, we need to assume that there is no simple case, there can be any general body. Okay, so that general body can have irregular shape. Let us assume the body is having irregular shape, and those are subjected to several loads, that is P1, P2, P3, P4, P5, P6, P7, etc. No geometry, random boundary condition, random loading. Now in this case, I want to, of course, under this general body, this is a general body. General meaning it can have any shape, any boundary, any type of loading condition. And under this general body is under equilibrium. Under the action of the external force, there must be some internal force produced, just like in case of bar, I know that there will be some internal forces that will be produced. So what we do is, we simply take one, to visualize this force, just take one cross section. Okay, so this is your cross section Mn, where I detach the body. Okay, cross section Mn, and I just divide this body into two parts, A and B, and I try to detect the body to see the condition of the internal forces. Now as long as, if I assume, I mean to resist the external forces of this part A, there has to be internal forces, and this may be the action of part B on part A, the material, because there are materials inside, right? So resistance is from materials, I mean depending on what kind of material is there, what kind of Young's modulus, that whether it is steel or concrete, or it depends on that. Okay, so action of the material that is acting on from part B on part A. Okay, so when I cut the body, I know that there has to be, from part B material, there has to be some action. Okay, that is there, the forces are distributed over the cross section Mn and part A. Of course, this has to be under equilibrium. It has to be under equilibrium again. Okay, and this has to resist the forces which are already there, P5, P6, and P7 and P. Now, as long as this distribution is uniform, okay, it is the same as this case. As long as if the stress is uniform, I mean I have already defined stress because continuously distributed forces. Now these forces can also be analogous to a kind of like हाइड्रोस्टैटिक फोर्स, यू नो प्रेशर फोर्सेस, या फिर कोई बिल्डिंग है आपके पास और यहाँ पे विंड फोर्सेस लग रहा है, ठीक है, वर्टिकल बिल्डिंग के फ्रेम पे ये विंड फोर्स है, तो विंड फोर्स कैसे लगेगा, पूरे सरफेस के ऊपर डिस्ट्रीब्यूटेड होगा, या तो फिर प्रेशर होगा, मैंने कोई पानी के अंदर कोई भी बॉडी को अंदर डाला, ठीक है, एंड देन वट एवर ऑन द सरफेस पे जो प्रेशर फोर्स है, hydrostatic force, wind force, so that will be a kind of, we can see that these forces are like analogous to that type of forces. Though this is internal, we are calling it stress, but that type of force and this type of force is same. Okay. Now, as long as this is uniform, I already know that definition, right? That is force upon area. But suppose this is the general case, because as we have already defined, this is the general case. Okay, this body is under general case. So we can no longer assume that this is a uniform distribution. So in that case, how do we define? Because it will be very difficult for us to, you know, if the stress distribution itself is irregular, and then how do I arrive at a concept of defining the stress? So we bring a concept of, you know, the stress at a point, sorry, stress at a point, okay. So let us consider any point on this body, O, okay. एक point हमने choose किया है, and now we need to determine the stress at a point. Of course, if I want to define the axis, I can define the axis X, Y and Z. That is okay, because this is the 3D body, 3D general body. There is no restriction on the dimension also. Okay, if 1D it is much simpler because this is 1D. 2D it is still, I would say, a complex, and 3D is much more complex. Okay, so this is a general body, and I can always define, because ultimately see I need to resolve my forces, because as long as I am able to find the resultant, and that resultant has some direction of the force, okay. But in civil engineering structure, whatever, like how do we write our forces? We resolve the forces along the, you know, Cartesian axis, X, Y, Z, that's the resolution of the forces. So here also, now I want to define the stress at a point, and then what I do is, let me choose some smaller cross-sectional area. So I am just defining a very small cross-sectional area. So in terms of differential language, we call these as delta A. Okay, आप इसको delta A बोल सकते हो, ठीक है? This is a smaller cross-sectional area. And when I want to, of course, the resultant, I mean the stress distributed over this smaller cross-sectional area, and I want to define the stress, I can define delta P, the force which is acting over this resultant force. Okay, resultant of this smaller distribution of the force, that is this smaller, means आप अगर ऐसे separate imagine करते, अगर ये मेरा D delta A है, and then these are the force distributed over small region, I can assume uniform, because this is a very very small length. See, basically larger structure है, उसमें आप uniform assume नहीं कर सकते, but आप एकदम small है, ठीक है, infinitely small, वहां पे मैं assume कर सकती हूँ uniform हो सकता है, ठीक है. So in that regard, I can assume that this is uniform, and resultant of this smaller distribution can be delta P. So that resultant may be in any direction, because it's a general body. ये जो delta P की direction है, वो कोई भी हो सकती है. मीन्स जरूरी नहीं वो x डायरेक्शन में या y में है या z में, ठीक है. सो द डायरेक्शन ऑफ डेल्टा p इज इन एनी डायरेक्शन, राइट. सो जनरलाइज वे, स्टिल जनरलाइज वे, I can define the stress as delta p by delta a. Now to define the stress at a point, how do I define? I try to contract the smaller area. Contract the smaller area, that is delta E. Okay. And the limiting value of delta E. Okay. So that limiting value is what? Delta A tends to 0. That's the limit. Okay. So if I bring the limit delta A tends to 0, and then I define this delta P by delta A, provided if delta A is 0, I can define this is the stress at point A. Now this is the definition. Okay, stress at a point. So limiting value of delta A means delta A को आप जितना छोटा करके जाओगे उतना आपको stress at a point मिलेगा. And that is the purpose that when I want to define the stress at a point, I just contract the smaller area and the limiting value of the delta A tends to 0, that will be your stress. Now what do I call this stress? I will call this stress as without limiting value average stress. Okay, that's the average. So I can write, okay, that sigma average is equal to this. Now second thing that we want to define, that I told you that direction of stress is same as direction of delta P. So delta P मेरा कहाँ पे act हो रहा है? पूरे ये surface में delta P can be in any direction. Okay, and the direction of the stress is same as direction of delta P. But this is not the final. I mean, this stress component has to be resolved into 3 Cartesian coordinates, axis. Okay, 3 means x-axis, y-axis and z-axis. So component of delta P in x direction, component of delta P in y direction, component of delta P in z direction. And the cross sectional area, whatever, let me call the cross sectional area. Now I will define these as a x surface. So x surface के ऊपर हमने एक ही, sorry, this plane is also cut in any direction. It may be inclined. जैसे ये बॉडी है आपका, उसको मैं inclined direction में भी कट कर सकती हूँ, ठीक है. The meaning of this is even this delta P and even the planes, okay. तो अभी ये immediately x surface define करना जरूरी नहीं है. हम सोच रहे हैं कि only the delta P has 3 components, okay, that is delta Px, delta, and if the here don't define the area of the x because I have to define the plane. Then can you, if the surface is inclined surface को भी आप resolve कर सकते हो, vertical, horizontal. अगर मुझे एंगल मालूम है inclined surface का, then also I can resolve into xyz plane. Okay, only thing is even the area, because area you can convert into x, y and z. So this is addition. Now this may look 1. That by definition stress at a point, it may look 1 quantity, that is limiting value of delta A tends to 0, delta P by del. But ideally it is not 1. That quantity is how many quantities that it can have? It can have altogether 9 quantities. And how? Because I will tell you exactly that, suppose I cut from top, I cut from front, and I cut from, horizontally. So there are 3 possibilities for me, x, y and z. And then I define my surface, that is x surface, y surface and z surface. On every surface, suppose this is your, now assume that this is your perpendicular to the x-axis. So मेरा इंक्लाइन है, उसने उसको मैंने ऑलरेडी रिजॉल्व कर चुकी हूँ, प्लेन को भी रिजॉल्व कर चुकी हूँ, मैंने वर्टिकल प्लेन डिफाइन कर दिया. नाउ दिस प्लेन आई विल कॉल इट एक्स प्लेन. Now how to define plane, that this is important, you have to understand. Defining plane, कोई भी सरफेस को आप कैसे डिफाइन करते हो, उसके परपेंडिकुलर जो एक्सिस है उसके बस. डिफाइनिंग प्लेन इन परपेंडिकुलर और आई मीन 90 डिग्री, और आप दूसरा वर्ड जो है मैथमेटिकली वो नॉर्मल बोलते हैं. हम जो नॉर्मल स्ट्रेस बोलते हैं ना, सिग्मा एक्स, तो नॉर्मल क्या है? नॉर्मल मतलब ये जो एक्सिस है ना 90 डिग्री. So any plane, suppose it is coming from here to here. Okay, so if the normal vector is coming out, that is 90 degree, that plane is x plane. तो अगर मेरा ये x एक्सिस है तो उसको मैं x प्लेन बोलूँ. सपोज ये मेरा y एक्सिस है और उसमें से मैंने वर्टिकल नॉर्मल दिखाया, then this is y plane. So similarly we can have 3 different planes. Now not only 3, suppose like okay this is x plane. Now suppose आप top plane लेते हैं और मेरा top axis y है. Okay, so this is 90 degree, y axis 90 degree going out. Okay, so we will call this y plane. And similarly let's say z axis, so मेरा ये front है और मेरा z axis ऐसे जा रहा है. Okay, and this is of course with 90 degree, so z axis, sorry, this is called z plane. So जो भी plane आपको define करना है, okay, उसको हम perpendicular axis पे, something wrong, okay fine. The normal vector coming out of that plane is defined by its plane. That means x-axis, y-axis, and z. Now if you imagine there are positives and negatives, आप कोई भी एक cube imagine करो. Right now let us restrict, I will draw that cube afterwards. But generalized case में you have possibility of 3 different planes. Okay, and on every plane you have possibility of 3 forces resolved. So अगर x plane है और मेरा यहाँ resultant delta p है, then I have delta px, delta py and delta pz. Now suppose I am considering y plane, that is top plane. So here also there is the possibility of delta p y, delta p x, delta pz. And here also there is a possibility of delta pz, delta p x and delta p. So 3 different planes, and on every plane you have the resolution of delta p component. Because why? Because this very small element, and we are not only element, we are defining stress at a point. But वो point के ऊपर आप imagine करो some magnified, you know, the cuboid. आप एक cuboid imagine करो जिसमें various planes है x y z, और वो डेल्टा पी जो है वो पॉइंट पे लग रहा है, लेकिन उसके जो रिजोल्यूशन है वो सारे प्लेन के ऊपर लगने वाला. सो वन पॉसिबिलिटीज, आप अगर देखते हो ये डेल्टा पी का जो रिजोल्यूशन कंपोनेंट है, हाँ ये जो एक्स प्लेन है, सो वन इज एक्टिंग इन द नॉर्मल डायरेक्शन बट 2 आर टेंजेंशियल टू द सरफेस. एक ये जो कंपोनेंट है, जस्ट ट्राई टू विजुअलाइज, इफ माई डेल्टा पी एक्स इज एक्टिंग इन दिस डायरेक्शन, these 2 are delta py, delta pz. But delta py and delta pz, see this is 90 degree coming out of normal, मतलब आप pull जैसे tension और compression, but remaining 2 are acting in tangential direction. So those are what we call, those stresses what we call कोई भी फोर्स अगर टेंजेंशियल डायरेक्शन में लग रहा है, what kind of force we call? So this delta B has first of all 3 components. On 3 different planes. एक नॉर्मल है, दूसरा क्या होता है, टेंजेंशियल डायरेक्शन में अगर फोर्स लग रहा है उसको क्या बोलते हैं? It has 3 components on 3 different planes and 3 different axes. So altogether we have 9 components. वो हम डिफाइन करेंगे, ठीक है? तो ये जो स्ट्रेस है, स्ट्रेस एट अ पॉइंट जो लिखा है, it may look 1 but there are 9 components. And this we may call it, this is not even vector. Like what is vector? Vector is a force and direction and magnitude. This we may not call vector because I have to define, when I define the force, it has a magnitude, it has a direction. Also it is, we have to define on which plane it is acting. So it is defined by its plane also. So 3 things: magnitude, direction and on the plane. So this stress is called as tensor, tensor quantity. उसको हम बोलेंगे second order tensor quantity. This we will investigate later on. I mean ये थोड़ा mathematical भी है और I mean it is slightly difficult concept to visualize, but by definition I am defining that how to define second order tensor and why. Why we are calling second order? Suppose मेरे पास एक force है. I just have a force. Then if I know, for example, this delta px, ये डेल्टा पी एक्स, उसको मैं फोर्स वेक्टर बोल सकती हूँ. क्यों? क्योंकि उसका मैग्नीट्यूड मुझे मालूम होना चाहिए और डायरेक्शन मुझे मालूम है एक्स एक्सिस. तो डेल्टा पी एक्स को मैं टेंसर नहीं बोल सकती. बट जो सिग्मा है, सिग्मा डिफाइन करने के लिए आपको डायरेक्शन, मैग्नीट्यूड एंड ऑन विच प्लेन इट इज एक्टिंग. So third quantity which is coming into picture, that on which plane, because there may be infinite plane. You are cutting the, you know, the solid body in an infinite plane. आप इधर कट करो, इधर कट करो, 360 डिग्री में आप कट करते जाओ. There are infinite possibilities of cutting the plane. That means we have to define the stress. To define the stress, we also need to have the information about plane, on which plane it is acting. And that is the reason why it is called as second order tensile, second order tensor. Okay, second order tensor quantity. So this is very, very important thing, very basic thing. Now we, as I told you, see this x, y and z plane. But if we imagine right now I have defined the positive x plane only. Positive. मतलब अगर ये x plane define किया, तो उसके पीछे दूसरा भी हॉरिजॉन्टल ऑपोजिट साइड में पैरेलल प्लेन होगा. सिमिलरली वाई प्लेन है ऊपर, तो उसके पैरेलल नीचे भी एक प्लेन होगा. सिमिलरली ऑन जेड, यू नो, दिस प्लेन एंड दिस प्लेन. सो देयर आर पॉजिटिव एक्स प्लेन्स, पॉजिटिव वाई प्लेन्स एंड पॉजिटिव जेड प्लेन. सिमिलरली नेगेटिव प्लेन्स, सो नेगेटिव एक्स, नेगेटिव वाई एंड नेगेटिव जेड प्लेन. सो व्हाट वी डू इज वी ट्राई टू now imagine the you know, one cube. I will draw that cube. That it is a magnified version of, you know, stress element. Stress element we can call. These sides of the cube are coinciding with the xyz axis, but stress at a point, मतलब ये point A है, ये point पे हमने stress define किया. बट मुझे एक क्यूब इमेजिन करना है वो जो पॉइंट के ऊपर ही है. आई एम जस्ट, आप अगर इलेक्ट्रॉन माइक्रोस्कोप में देखते हो, इफ यू रिफर टू माइक्रोस्कोप, इलेक्ट्रॉन, you can get the smaller thing into larger scale. And similarly here also I have to visualize a stress cube which is very small. Okay, it's very very small, but to define my stress tensor, all the quantities of stresses I have to visualize this. Okay, and that is the reason I am visualizing this stress cube, and that will help me in organizing my stress component, the notations, proper notice. So right now what we are defining is notation of the stress. So let us imagine one cube where I have, so first we write notation. This is very very important because in civil engineering positive and negative signs, we have to be very particular about positive negative signs. So we have to define all the notation properly. Okay, so notation of stress component. So if this axis is coinciding with the xyz axis of the cube side, so x, y and z. Okay. And sorry, not this. Okay. So this is my x plane as we defined x plane. How we have defined, because positive outward normal perpendicular, this is your x axis. Then this is your, let me write, this is positive x plane, this is negative x plane. Similarly, this top is positive y plane and bottom is negative y plane. This is your positive z plane. This is your negative z plane. Now I write the delta px, that is the force component of this. Let me define, this is the normal stress. So on every plane, we have three components of stress. I mean, if I want to write force, then multiply by, delta p by over. So I can write force also if I am able to multiply it with the cross sectional area. So sigma से आप अगर sigma x लिखते हो, but उससे cross section multiply तो वो delta p x हो जाएगा. ठीक है, something like that. So on every plane we have three components of stress. One, normal. Normal means it is just like your tension compression. And 90° to the surface. Second component when we want to define shear stress. So जो मैंने टेंजेंशियल डायरेक्शन में आपको बताया ना, जो कंपोनेंट आपका टेंजेंशियल डायरेक्शन पे जा रहा है, shearing stress, which is acting parallel or tangential direction to the surface. So on every plane I have three quantities. One is acting normal, that I will call it this at sigma x. So जो हमने डेल्टा पी एक्स यहाँ पे डिफाइन किया था, आप यहाँ पे देखो, ये डेल्टा पी एक्स हमने डिफाइन किया था. If I multiply that with the cross sectional, divide it by cross sectional area, then I can get sigma x. Okay. Now the length, side length will be of course delta x, because I forgot to tell you one thing, that because we have already defined limiting value, this does not remain as sigma average, that it's delta sigma. ओके आप उसको लिमिटिंग वैल्यू करोगे तो आप सिग्मा लिख सकते हो, सिग्मा एक्स. ठीक है, तो इट इज इफ इट इज एवरेज इट इज डेल्टा सिग्मा होगा अगर एवरेज होगा तो. बट अगर उसको डेल्टा ए को कॉन्ट्रैक्ट किया स्ट्रेस एट अ पॉइंट तो हम उसको सिग्मा लिख सकते हैं. ठीक है, सो दैट इज द रीजन व्हाई आई हैव रिटन सिग्मा एक्स ओवर हियर. Now remaining two, I can define in the tangential direction because मेरा डेल्टा पी जो random direction में था या जो भी वो फोर्स था उसको मैंने फोर्स को रिजोल्व किया and then when I divide it by the cross sectional area I get the stress. But ये जो sigma p था उसको मैंने on every plane I have resolved into three different components. And then consequently I am finding out the stress. So that now this sigma is not there because in civil engineering also we write the components. Ultimately resultant anyway should vanish क्योंकि equilibrium है तो resultant zero होना चाहिए. हाँ राइट. सो हमें और हम इलास्टिसिटी ये जो सब्जेक्ट है एडवांस सॉलिड मैकेनिक्स इसमें बेंडिंग मोमेंट वगैरह बाद में आएगा बट पहले हम स्ट्रेस और स्ट्रेन को डिफाइन करेंगे. जैसा स्ट्रेस है वैसा स्ट्रेन भी आएगा. ठीक है, इन एवरी डायरेक्शन. सो फर्स्ट वी विल डिफाइन स्ट्रेस एंड देन स्ट्रेन. सेकेंड कंपोनेंट आई एम कॉलिंग इट shear stress because it's acting in the tangential direction and I have resolved into y direction, right? And third one I have resolved into z direction. So these I may want to call tau and tau. These both are shearing stress component. But how do I differentiate this component and this component? So always, whenever I am writing notation for the stress component, it is easy to interpret sigma x, sigma y and sigma z. Similarly, like sigma y आप यहाँ पे define कर सकते. ठीक है, sigma z जो है आप यहाँ पे जो normal है वो define कर सकते. So उसमें positive negative क्या होगा? Tension अगर है तो positive, compression है तो negative. Sigma x अगर ऐसा जा रहा है तो it will be compressive. तो यहाँ पे opposite direction में होगा तो वो कंप्रेशन होगा. दोनों साइड पुलिंग होगा. एक साइड से पॉजिटिव प्लेन से राइट में जा रहा है, नेगेटिव प्लेन से लेफ्ट में जा रहा है तो उसको हम टेंशन बोलेंगे. सिमिलरली ऑन सिग्मा वाई upward and downward, so and sigma z upward and front and behind, that is this. So sigma is easy to understand, but how do we define tau, that is notation for the shearing stress component? So I have to define shear because on single plane there are two shearing stress quantities. That means I need to define two subscript for the shearing stress component. One, the direction, and second, on which plane it is acting. Okay. So shearing stress is defined by two subscript. This is very important. So what is first subscript? Suppose tau, first subscript define, let's say tau xy. अगर ऐसा है, what is the first subscript says? On which plane it is acting. And I mean the first subscript and second subscript in which direction, that is this is your second subscript, this is your first, this is your second, this y is second subscript, this is your first subscript. So second subscript defines in which plane, in which direction it is acting. So it is very easy to define now the shearing stress component. It's very simple that this tau, now I need to define this is on which plane it is acting. So first subscript by default comes tau x. पहला यहाँ पे भी ये जो एरो है उसको tau x में फर्स्ट सब्सक्रिप्ट लिख दूँ. Second subscript we have to write in which direction it is acting. So yx. और ये जो होगा xz. So we can write these similarly on other 3 planes, other 6 planes rather, but positive plane में हम लिख लेते हैं. So ये positive plane में, because the sign convention which is shown in this cube is positive, but इससे reverse होगा, सारे arrows उल्टा हो जाएंगे. Every arrow will be reverse, then it is negative. So I will tell you the significance of when shear stress is positive, when shear stress is negative. Okay. Similarly, I define on this plane, top plane, that is y plane. I am not showing the front and behind. I mean, if you want to show, you can show. ये tau xy आपका bottom जाएगा यहाँ पे, क्योंकि ये right negative x plane में वो नीचे जाएगा. फिर tau xz जो है वो उल्टा ऐसा जाएगा. ठीक है. Now on top surface I have these 2 components. So right now I have shown the positive plane and positive direction. Okay. So when do you call shear stress positive? When all the stresses, when do you call shear stress positive? See, normal हमने already define कर चुके हैं, compression and tension. So अभी tension में है तो सारे positive है. But when do you define shear stress positive? When stress is acting on positive plane in positive direction, stress acting in positive plane and positive direction. But if stress acting in on negative plane and negative direction is also positive, क्योंकि ये पूरा सेट है, आप देखो पूरा जो क्यूब है ना वो पॉजिटिव डायरेक्शन में, सो नेगेटिव प्लेन में नेगेटिव डायरेक्शन में लग रहा है ना, तो बट वो मेरा पॉजिटिव साइन है. जैसे शियर फोर्स में आपने देखा होगा, बेंडिंग मोमेंट और शियर फोर्स डायग्राम प्लॉट करते थे आप, तो देयर वर पेयर ऑफ शियर स्ट्रेस, शियर फोर्स, मतलब आप पॉजिटिव किसको बोलते थे, अपवर्ड एंड डाउनवर्ड. तो ये क्या है, ये नेगेटिव प्लेन है तो उसमें डाउनवर्ड जाएगा, पॉजिटिव प्लेन है उसमें अपवर्ड जाएगा. तो दिस इज माय पॉजिटिव शियर. ये आपने जब बेंडिंग मोमेंट शियर फोर्स डायग्राम करते थे, जैसे पॉजिटिव मोमेंट में कैसा था, क्लॉकवाइज एंड फ्रॉम हियर क्लॉकवाइज एंड फ्रॉम हियर एंटी क्लॉकवाइज, लेफ्ट एंड राइट. So it is something like that. Okay, we have to follow this sign convention which is proper. So stress acting in positive plane and positive direction is positive. Stress acting in negative direction, negative plane and negative direction is also positive. And the vice versa, इससे उल्टा, मतलब positive plane negative direction, negative plane positive direction, so vice versa is negative direction. So this you have to keep in mind regarding shear stress. Now what will be the, I mean we write the remaining components, so this will be tau, yeah, tau y x, this will be tau y z, and similarly here you may write एक component ऐसा आएगा, एक component ऐसा. So tau z, z y, and tau z x, and similarly you may write on the back side. So this is called your stress element, 3D stress element, 3 dimension. Now as long as definition is concerned, now if I want to define, I can also write the components. मतलब आप डेल्टा पी एक्स है उसको पी एक्स अगर नॉर्मल फोर्स है तो उसको आप डेल्टा पी एक्स बाई डेल्टा ए कर सकते, डिपेंडिंग ऑन विच प्लेन इट इज एक्टिंग, वो प्लेन के हिसाब से आप एरिया भी वो प्लेन का एरिया ले सकते. एक्स प्लेन है तो एक्स रहेगा, ठीक है। सिमिलरली डेल्टा पी वाई है तो डेल्टा ए वाई, क्योंकि वो जो नॉर्मल स्ट्रेस होगा वाई प्लेन पे लगेगा, एंड डेल्टा पी जेड होगा तो डेल्टा ए जेड होगा। तो ये तीन कंपोनेंट नॉर्मल स्ट्रेस के होंगे। रिमेनिंग 3 को डिफाइन करने के लिए आप टाउ को डिफाइन करने के लिए आप डेल्टा एक्चुअली इसमें सब्सक्रिप्ट के साथ होगा, मतलब शियर फोर्स जो आप डिफाइन करते थे, शियर फोर्स, ठीक है। ये जो P है नॉर्मल फोर्स है और V है शियर फोर्स होगा, तो उसमें आप एक्स वाई और ऐसे करके डिफाइन कर सकते एक्स वाई, क्योंकि शियर फोर्स कौन से प्लेन पे और कौन सी डायरेक्शन। सो डेल्टा V एक्स वाई है तो वो कौन सी डायरेक्शन पे जा रहा है, V वाई एक्स है अगर, तो ये है आपका कंपोनेंट। V एक्स वाई है तो ये कंपोनेंट है, ठीक है। सो अगर मैंने एक्स वाई लिखा तो ये जो मेरा अगर शियर फोर्स ऊपर की डायरेक्शन में, ये डायरेक्शन में शियर फोर्स है टाउ एक्स वाई, सो टाउ एक्स वाई मैं कैसे डिफाइन करूंगी, यहाँ पे लिमिटिंग वैल्यू ऑफ ऑन विच प्लेन इट इज एक्टिंग, दैट इज डेल्टा ए एक्स, एक्स प्लेन के एरिया जो होगा, और डेल्टा वी एक्स वाई दैट्स द फोर्स, and this delta ax tends to 0. So this is my tau xy. Similarly, बाकी जो 6 कंपोनेंट है आप डिफाइन करें, टाउ वाई जेड, टाउ जेड एक्स, ठीक है, एंड देन वाई जेड विल बी एक्टिंग ऑन वाई प्लेन, तो डेल्टा ए वाई हो जाएगा, ठीक है, टेंस टू 0, एंड डेल्टा बी वाई जेड डिवाइड बाई डेल्टा ए वाई, yeah, and similarly delta az tends to 0 limit, and then I have sorry, here you have to define, and then we have equal to delta v zx by delta az। ऐसे करके बाकी जितने भी shear stress कंपोनेंट है हमारे पास 6 shear stress कंपोनेंट है, 1 2 3 4 5 6, we have 6 shears, so remaining you can write, okay, remaining you can write. So 6 shear stress component. Remaining, please note down. Six shearing stress component plus 3 normal stress component. Okay, now we need to see that what is the effect of this shearing, positive shear and negative. अगर मुझे कोई एक एलिमेंट सिर्फ ये विजुअलाइज करना है, what will be the effect of positive shear stress and what will be the effect of negative. So you again imagine the cube where you just have the only shear stress acting, okay, only pure shear. तो वो जो क्यूब है उसको हम प्योर shear बोलेंगे। Okay, if this is positive, this is positive, this is positive. Positive मतलब positive plane positive x, okay, and negative plane negative. Just एक ही समझने के लिए एक ही दिखा रही हूँ। Similarly on positive plane positive direction, negative plane negative. So this is my sign. Now what will be the effect of this? This under the action of this shear force or shear stress, whatever you want to call, it will try to, this will try to slide, you know, and the top and bottom surface is also try to, you know, basically this will distort the element. Okay, so what distorted element कैसे दिखेगा आपको? It will look something like this. Rhomboid जैसा दिखेगा. It will be a kind of rhomboid. Because these are positive set, indirectly I may say this will produce shear strain. So what is the meaning of shear strain? Change in the angle, the distortion. Okay, change in the angle means earlier it was 90 degree here. This is now less than 90 degree. And this I may call gamma or gamma by 2, assuming both are same, like, so 90 minus gamma. That's your, if the side ABC, okay, if the angle between AB and BC reduces, I can say positive shear stress or positive shear strain. Even the shear strain positive कब define करना है? 90 minus gamma. Similarly on the opposite side, right? Opposite में 90 minus gamma. But side this ABCD, side AD and AB, it will be 90 plus gamma, right? क्योंकि ये 90 degree यहाँ है और ये, so this whole angle will be 90 plus gamma. Then this is positive. Now negative की effect क्या होगी? The reverse. So angle between AB and BC, आप उसको imagine करो कैसे वो distort होगा, opposite direction. Means आपका ये वाला ऐसा बढ़ जाएगा. It will be something like this. Right. This will be the distortion that has taken place. I mean, this figure is not very perfect, but आप यहाँ पे देखो, ये जो मेरी ABC साइड थी, अगर मेरा उल्टा स्ट्रेसिस है, अगर क्यूब लिया मैंने, यहाँ पे डाउनवर्ड है, ठीक है, यहाँ पे ऐसा है, दिस इज like this, equal and opposite actually, दोनों साइड इक्वल है, तो एक ऐसा हो जाएगा और दूसरा ऐसा हो जाएगा, ठीक है. So if the angle between AB and BC increases, that is 90 plus gamma, then it's negative shear strain. Okay, this is negative shear strain. And similarly the opposite, and then if this becomes 90 minus gamma, also negative shear strain. So entire pair, this pair of shear stress is negative, and this pair of shear stress is positive. Okay, I think today I will cover this, and any doubt here, any questions? Online में किसी को doubt है?
No.
Okay.
No,
Have
ma'am.
you? Okay, fine. Okay, so today I think I will stop here, because see, we have defined stress at a point. How many stress component? Why stress is called as a stress tensor? Because three things: magnitude, direction, and the plane. And how many components of the stress? And then notation of the stress, direction of the stress. And next class we try to investigate further that first we need to prove that you can see here tau xy and tau yx. So I need to prove tau xy is same as tau yx. Then it reduces further, instead of 6 shearing strain we have 3 shearing stress component. So we try to prove that, and later on we will see how, like, there are many things here. So this is basic, very fundamental. I think today I will end my class here. It's a 1 hour. I think your next class is there. I think Nirav sir.